Okay, my friends, I'm sure if you've been with me for a while, you know about my dipole electron flood theory and the evidence to support it. Now, we did what they're talking about right here, a new way to achieve nuclear fusion. Well, nuclear fusion, let's talk about what it is and how they're going to do it. And they're going to use plasma, which is basically what we used. It's almost the same thing. Okay, so what we're discussing here is a new way to achieve nuclear fusion. And this is from a company called Helion. And he's going to give a little explanation of the setup. Where do you see this? Here goes.
For what this machine is. Yes, so you're at Helion's Redmond facility. Here we're standing in front of our 6th generation machine. We call this one Trenta. This is the 6th generation of machines that form, merge, and compress fusion plasmas to fusion conditions, doing fusion.
All right, you hear what he just said. A compression to fusion conditions, creating plasmas to fuse back together again to create fusion. All right, remember this one. They're creating plasma at both ends, and then they're going to squirt them together and make a collision. Okay, so here they are again. They're squirting these two plasma rings together. All right, and here's what he has to say.
As the plasma passes by, traveling at millions of kilometers per hour, to push it even faster towards the center. That would be impossible without...
All right, and then they're going to go into how they technically achieve this to keep it crushed in the center, trying to create fusion of this plasma. Well, let me show you something. All right, think about what he's talking about now. They're making this collision, and they're putting it into a magnetic trap. Now listen to what he has to say. Well, just let him talk. Here goes.
In the center, which proceeds to shrink until the ions trapped within it have nowhere else to go.
When he says it proceeds to shrink, it's coming into the venturi and it's, boom, right next to each other, and they're just crushed into a ball. Now he's saying that they are electrons. I believe I just heard him say that. All right, so this is what Helion is doing. Astounding sequence of events. Here it goes.
Cause fusion in this machine is a delicate symphony of electronics, pushing two plasma rings into a violent collision and catching that collision in a magnetic trap in the center, which proceeds to shrink until the ions trapped within it have nowhere else to go but to fuse.
All right, now he's calling them ions. Well, let's see what an ion is. All right, so we know ionized just means you have extra or not enough electrons, so it's charged. Well, light is only the charge. It has nothing to do with this big chunk. Light is down here, so light is not plasma. All right, but plasma is a state of matter that emits light. Plasma is when they break these things up and it shoots out a piece of light. All right, plasma is a high energy state where the atoms, which they use, we don't use atoms, we use light to begin with. So the plasma is a high energy state where atoms are ionized. That means that the little pieces are knocked off. We're starting with these little pieces. We don't have to ionize anything. So it results in light emission. We're using light to start with. So light is a type of electromagnetic radiation. Now this is where they're totally wrong. It says light does not occupy space. It absolutely does. It has no mass. It absolutely does. It has a volume. It absolutely does. And is therefore not considered matter. Light is matter. Every single thing there is made of the particles of light, which is a muon and electron neutrino. I'll show you right now. First of all, let's just start right here. This is Fermilab, CERN, all of them do the same thing. They collide these huge things together, like are these, and they smash them to bits, and they can find these tiniest particles. The black one never changes size, has a glowy edge around it. The glowy one has no mass to it whatsoever. I agree with exactly what they're saying here because we found those particles using light. We didn't start with these and getting all kind of debris. We started with these, and when they broke, we could see the black and the white. I'll show you right now. What I just showed you was Fermilab showing their point particles. This one right here is the point particle. This one here is the fixed particle. That one never changes size, never. It stays the same no matter what you do. This one can get big, it can get small, and it has all the energy. This has all the mass. And here's what they look like when they came through as light. That's light. So don't tell me this has no mass. And that's the energy. And the only way the energy can move is to be pushed by the carrier. This has no weight. It can't move anything out of its way. This is what moves it. This is what it looks like, and this is how its energetic values look. So this is getting pumped up because it's interacting with those particles in front as it moves this way. That's the black ball that they show Fermilab. It's identical. There is no difference because we started with light. They had to end up with light by smashing these things into bits. We started with light so we can see it. And they don't know that this is what light consists of. They still have no idea. All right, now here's our light coming down the stream here and accelerating due to this venturi. At this point, you can see the actual particle pulling itself right out of the wave. It's being accelerated so fast. Here, when it hits, remember we had a black and a white? When it hits, the black can't get through. The black stops here and the white showers through. Exactly what they say at Fermilab and CERN. These are sterile muons, and this is where the white showers right through. Electron showers. All right, so we started with light. We didn't have to create all kind of plasma and then try to make it fuse back together. This is fission and fusion. There's no other way to look at this. There's absolutely no other way to look at it other than this is fission when the black separated from the white, and it's subatomic nuclear fission. These are parts of the nucleus. These are the tiniest little bits and pieces. These are smaller than the atoms. Atoms are up this gigantic like this, but they consist of like a whole batch of these. That's what dipole electron flood theory is all about. Dipole electron flood theory says that there's 1,824 particles seem to become neutral and stable at 1824 for some reason. Boop, and they lock in. All right. If you have too many, they will end up giving them up to try to get back down to 1824. If you have too little, they want some more to get up there. That's what stability is all about, and they call those half-lives. And they're only half-lives because it just doesn't have enough little bits and pieces in the nucleus to make it stable. It wants more, it wants to give some up. That's what half-lives are all about. And I'm showing you that we started with light, split it, and put it back together again. Fission, fusion. All right, so don't forget my claims about this. We started with light. And light is not plasma, they say. I can go along with that. Light is a stream of particles. It's just a stream of subatomic particles. And when they get in, when this happens to them, they turn into plasma. Which, to me, plasma at this point in my mind is the separation of the black from the white. That's plasma. Now, they say plasma to them is shooting off one or two little particles of these. That's not to me. Plasma to me is when all of those separate and they turn into the black and the white. Now, that's like a bar magnet breaking in half, and it cannot happen until you get down to this level where you're at the subatomic dipole level. And there you can break them apart, and the white will stay this way and the black will stay this way, and that's how black holes get created. And they made one in space. The Russians did. Here it is. Yeah, I'm telling you right now, that's a black hole in space they made just by accident when they injected all these charged particles into a vacuum chamber. The dark went right to the center. And now this is exactly my prediction of what a proton looks like, and all elementary particles. They have a certain mass inside, which is the dark matter, and surrounding that is all the electrons. All right, and that's what a proton would look like, is the dark matter would be in the center and all the electrons would be around it, and the electrons bounce back at you. That's why they could never see the dark matter inside. But that's what gives everything weight. Everything weighs something, and that's the dark matter. The glowy part really has no weight to it to speak of. You see this? These are the physics of electron showers. They use protons. Don't forget, they're using big particles, protons, banging them together. Now, they get a large number of hadrons, which are little chunks, along the beam collision axis, and the decay of hadrons creates large flux of high-energy neutrinos. I showed you those, the muon neutrino, electron neutrino. Now, the neutrinos and anti-neutrinos of all flavors, the reds, the greens, the blues, the this, the that, this is called the electrons and muons. Yes, the energy of the neutrinos interacting within this phasor creates from a few 100 billion electron volts to trillions of electron volts. That's how much this explosion of electrons and muons creates, and that's precisely what we did. This is them right here. Muon neutrino and electron neutrino. Electron neutrino turns into the showers exactly like I just showed you, but with trillions of electron volts. And right here we need to harvest it. I'll show you in a second. And the muon stays black and goes on its own. This is what we want right here. This is the energy. You know, the black is just the weight. But that's where all the weight comes from. That's why things weigh something. Is because of the black dark matter, which is inside. Hold on a second, let me show you something. This thing is just unbelievable, this thing they're doing here to try to create that energy. Hold on, I have my dipole flood theory right here. This is what a proton really looks like. It looks like this. And all of the outside particles are the energy. And way in the center, there's like a black ball inside there, which has, I believe, the same number of particles as the white ones. And of course, they start blue, green, and red. The tighter they are is blue. When those take off and get ripped away, they're gone. And the same thing with the green. But the red doesn't always go. It sort of hangs around out there because it's not quite so tightly held to the core. When you break that thing apart, you got some energy. And that's what the atom of a proton is. And there's approximately 1,823 dipoles. A neutron is 1,824. And these are the two particles. That's all that exists. These are only two particles that exist. The white one and the dark one. And added together, this is what I call atomic vapor. All right? They can separate. We know that for sure. I've shown you. And we know that they glue together as electrons and photons. Right, there's the electron. When the two of them glue together, and they glue up and down, they don't glue sideways. All right, and then two of them side to side make a photon. That's a gluon or an electron. And that's all that exists. Everything there is made of this. Everything there is. Not a single thing isn't. But they don't become stable until they hit certain places. So you have a ball of these, like this, and the first one is hydrogen. And that's about 1,825 or so in a ball. All right, now when you get to helium, you're already up to 7,300 and something like that. Because for every proton, it's 1,823, and for every neutron, it's 1,824. So you have to multiply the number of neutrons and protons that are in all these, and that's what you get, the real atomic mass. All right, and then now this is going to change some things, and the periodic chart's going to change. Chemistry a little bit, space a lot, distances in space-time a ton. Redshift is just slowing down light as it comes to us. And I can show you that too. All right, I've shown you this one here, which is the red photons. And here's they are in the neutrino stages, and then this is the photon, and then that's when it explodes. The green is exactly the same, only it's much faster. And here's the neutrinos down here, and there's the photons up here. And the two of them together going through the same slit at the same time comes through here. The green one's up here, and the red one's down here. And you can see how weak the red one is compared to the green one. The green one reconcusses way out there. It's quite obvious where the energies and the particles. These are particles, no question about it. And here's what they are. And the muon neutrino is the black one. Electron neutrino comes through and turns into a shower. It's exactly what you want to see and exactly what you did see. All right, you could hear they come when they come through the venturi. The black one stays back, the white one showers. And here's the whole event happening all at one time. We want to put our harvester right there. And then we can harvest, I think we can have as much energy as you want right there. So the laser is shooting the pulses here. The black can't get through. Just the white comes through. We squirt it down into the battery. Put the collector right here. Photodiode, let it all collect through into the whatever user, whatever. And that's the circuit. Now, we can use a little of this to keep the laser going. We can carry this around in here. You don't need any gigantic equipment for this. This is very simple, very easy, and we're not starting with things like this. We started with this. So we're down here where they wanted to get to, but they have to do all this gyrations to get down to split all these things apart and bundle them up and add billions of amps of electricity. I mean, they heat this thing up so that it just vaporizes by itself, and then when they get that energy back, they think they collected something. It's just getting back what they put in, if they're lucky. I don't think they've ever broken even yet. So don't forget, this is our whole equipment. It's just a laser shooting through a venturi here. And then we'd have to put some kind of a receiver right there. That's it, we're done. I mean, you know, you got to spruce it up a little bit and put enclosures and make it so that it funnels in and does all the things the right way. So you capture all of that energy. But this here, you could put in a little, you know, as I showed you that thing, like it was a Geiger counter, but it's basically, you should be able to put it in something like this, and you have all your plugs right in there, your dial, anything you want, AC, DC, you know, USB, whatever you want in there. Once you collect that energy, and that white energy, that is powerful, and I mean powerful. Whenever you see that, whenever you see high energy illumination, the more luminous, the more power. And you can see it's fighting back against all the other particles that are coming this way, because it's literally a subatomic nuclear explosion. That's what it is. It's a subatomic nuclear explosion. These fields are here, just like this one is, but this one's, you can see it because it's being pulled forward. These you can't see because they're just going at normal speed, but now they're being pushed back at by this. If you can see back here, you see all the reverse lines there? That's how explosive that interaction is. That's a subatomic nuclear explosion. All right, let's sort of conclude this. In the atmosphere, we get cosmic radiation coming down, and they cause air showers of extensive cascades of subatomic particles and ionized nuclei. Ionized, we know what these things mean now. Now, a primary cosmic ray enters the atmosphere. This is a really, you know, it's just a particle, and it's coming really fast. When a particle of cosmic radiation, could be a proton, a nucleus, or an electron, even a photon, or rarely a positron, interacts with the nucleus. Now remember this, the nucleus of a molecule in the atmosphere, it produces a vast number of secondary particles which make up the shower. The secondary particles are the separated particles, the black and the white. We are separating them using light, so we don't have to use anything other than just shoot them through that venturi, and we have created these secondary showers. Now, when you separate the white from the black, that's when you have your energy. That white is just raw energy. And you can see it when an atomic bomb blast goes off. The house just burns up because the light hits it first, and then a second later the whole house goes when the black particles catch up. Okay, this is confirmation of what I just said. The white particles surround the black. When they take off from a nuclear bomb blast, they hit things first and everything vaporizes. Then the black from way inside bashes and knocks things over, because that's the only thing that has any weight. And this confirms it right here. This is Teapot Apple II Q House atomic bomb effects. They set this all up to see what would happen when they set off an atomic bomb. They have a hardened enclosure facing towards the destruction, so it's not getting hit by the light, so I can see everything. And you'll see it just burns. Well, I'll show you. Here it goes. This is running real slow motion. Boom. It vaporizes right now. You see this? It's just vaporizing. It's nothing's even moving. The poles and everything is just vapor. The electrons, which have no weight whatsoever that I can determine, are just infusing in there and saying, whoa, 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 and all of the combustibles are moving out as that particle infuses its way in. And they're just dusting off. Now, shortly, when all of this stuff is vaporized and it's just about to go, boom, there comes the black particles. Completely two separate events. The white ones go first, the black ones come next. Okay, I'm going to leave it at this. Copper, you know, is used to conduct electricity. Well, why does it conduct electricity so well? Why does that conduct so well? Well, here's why. Because these are all these isotopes that are inside of copper. They have all these extra or not enough electrons. They want to give a bunch up or take a bunch in. And all of these are different. The same copper, it's copper, but they're all different isotopes. And all that means is they have less or extra electrons. That's all it means. And then down here, they're stable. Down in here, they're stable. They don't want to give any up, and they don't want to take any on. All right, so that's what nuclear physics is all about. It's stability of, it almost shakes until it hits a certain zone, and bing, then it becomes stable. It's got exactly the right number of electrons. For some reason, they just stabilize at that quantity. So anyway, there's more work to do, but what we're thinking about right now is just not right. The way they're talking about light having no mass and it's not matter. It is, light is atomic vapor. It condenses into matter. Light is like these little bits right here. And if you have enough of them together, you get a proton. You get a bunch of protons together, you get some kind of molecule. But it all starts with light. Light is the atomic vapor. That was my theory in 1970, and it still holds true, and it will forever. All right, love you all. Thanks. Bye.